Greetings and welcome to the introduction to astronomy. In this lecture, we are going to talk about impact cratering. Now, we've looked at craters on the Earth and a little bit at craters on the moon. And we want to kind of summarize a little bit about how this works and how impact craters are formed. We certainly have the general idea that it is formed by an object smashing into another surface. But we do want to look at that in a little bit more detail here. So what do we have when we talk about craters? There are multiple types. There are volcanic craters, such as pictured here, which is Crater Lake in Oregon in the United States. And that is the caldera of a volcano that has become a lake. So that is a volcanic crater. So craters can be caused by volcanoes. And we have impact craters, which are caused by impacts. So here we see Meteor Crater in Arizona, and that is an impact crater. Now, other than the one being filled with water, we can see that there are a lot of similarities between the two. And on Earth, we find both types. We can find volcanic and impact craters. On the moon, we pretty much find impact craters. So let's look at how the crater forms. First of all, A is just the object coming in. In B, we actually get the impact. So here we have the object impacting the surface. Now then what happens is the intense heat. We have a conversion of energy here. The meteor had a lot of kinetic energy, that is energy of motion, traveling at very high speeds. And that energy is all of a sudden gone, because it stops. So it has no kinetic energy as it strikes the ground. And then it will convert that into other forms of energy, such as heat and other things, throwing this material back out. So it is the evacuation stage here shown in C, where material is thrown out of the crater caused by the shock wave of the meteor impacting. Then we see in D what happens afterwards. So long after the crater has formed, material begins to collapse back into the crater. So eventually there will be less of a crater than there originally was. So a nice sharp crater is relatively recent. Now the final stage not pictured here is modification of the crater. Weathering effects will modify this, and that will slowly wear it down. On Earth, that could be wind on water. On the moon, that would be things like micrometeorite impacts that cause slow erosion of the crater. How big is a crater? Well, let's look at an example here. And we can look again at one of the craters on the moon. And here we see the crater, and the crater is going to be about 10 times the size of the object and about twice the depth. So if you had an object that was a kilometer in size, it would form roughly a 10-kilometer crater 2 kilometers deep. So the damage done is much larger than the object itself. So you can imagine as that gets bigger and bigger, if you have an even larger object striking, it's going to form an even bigger crater and an even deeper crater. Now when we look at some of these relatively new craters, let's look at a relatively fresh crater on the moon. This one is pretty new, but here's an even newer one shown. And that is because we can tell that we see the impact crater here, but we can still see the rays coming out. So the crater rays are ejected material that expands out to a large distances away from the crater. We also have an ejecta blanket in close. So that's in right at the crater itself, we can see. And that is material thrown out by the explosion. We can see it's a much lighter color as it was expelled outward in the massive explosion that formed the crater itself. We can also get secondary craters. So that impact can throw material out, and then other material that can form secondary craters. Now we notice with all of these craters is that they are essentially circular. That doesn't mean that objects hit the moon edge on. When an object explodes inside the moon and sets out that shock wave as it hits the surface, that will always form a circular crater, even if the meteor happened to hit at a not quite direct angle. So even if it's off a little bit, it will still form a circular crater. And we can look at a few more craters here. And we see that again, they're circular. And what we're really looking at here, we want to think about, we've talked about determining ages by crater counts. Well, crater counts are one way to be able to tell how old something is. The more craters we see inside a crater, for example, the longer that crater has been exposed to space. Now we can also see overlapping craters, and that can tell us relative ages of the craters. Certainly any crater inside another crater had to have formed later. It would not have survived the impact. So these craters that we see inside other craters would then have formed later. We can also see that sometimes craters overlap other ones. So this crater seems to overlap the larger crater. So it must have formed later. Otherwise it would not have, it would be the one damaged and not the larger crater. So we can look at how craters overlap each other to really get an idea of which ones came first. Crater counts will give us a better estimate of the age. And if we want to get the actual ages, recall how we did this. We needed a sample of the rock to determine through radioactive dating methods to figure out how old that crater actually was. Now, how often are things cratering? Well, let's take a look at this. Typically, we look at rates of formation here, and there would have been some kind of maximum here. We really don't know what happened in the early stages. It's really hard to tell. There were so many objects around impacting. So really, if the cratering rate were constant, then the highlands would be older than the universe. So we know that the cratering rates have decreased drastically over time. They were much larger in the past and much smaller today. However, they are about the same within the solar system. They are consistent throughout the solar system, meaning that while they change, this graph works just as well for Mercury as it does for our moon, as it does for a moon in the outer solar system. So we can use something like this to determine ages throughout the solar system, even if the objects are not close together. And what we see is that there were higher cratering rates in the early history, lots of cratering going on here. But for the last 3 billion years, cratering rate has been essentially constant and very low. So while it's still going on, we get nowhere near the impacts over the last few billion years that we did in the first billion years or so of the history of the solar system. So let's go ahead and finish up with the summary. And what we found and talked about, we talked about volcanic and impact craters. Impact craters being created when an object strikes the surface and explodes. And the number of craters that we see on a given surface can tell us about the relative age of the surface. So we will use this when we get to other parts of the solar system, when we look at things like Mercury, Venus, Mars, and the moons of the outer solar system. We will come back to this to learn relative ages of the different surfaces in the solar system. So that concludes this lecture on impact cratering. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.